Hello everyone, this is Mohan Gowda studying in Sri Venkateswara College of Engineering. So here is my presentation on Quicksort. So here is some brief information on Quicksort. Quicksort is a fastest known sorting algorithm in practice, and it has a best case and worst case analysis. And in average case, the n log n, we don't prove it. So in worst case, n power 2, but the worst case as slideum happens. And another divide and conquer recursive algorithms like Quicksort. Divide steps and Quicksort divide steps like picking an element in pivot V in S and partition into two disjoint groups like S1 and S2. And here are some steps like conquer steps and combine steps. In conquer steps, recursively sort like S1 and S2, and combine step includes the sorted S1 by the time returned from the recursion, followed by V, and followed by the sorted S2. There is nothing extra needed to be done. And here is some to simplify the many. We may assume that we don't have repetitive elements, so to ignore it equally case. Here is some basic examples of Quicksort. And what is two key steps like how to pick a pivot and how to partition. Picking a pivot, use the first element as pivot if the input is random, okay, and if the input is restored or reverse order, and all the elements go into S2 or S1, and this happens consistently throughout the recursive call, and the result in power 2 behaviors like analysis this case later, and choose the pivot randomly, and it is generally safe, and random numbers generation can be expensive. In place of partition, if an additional array like Quicksort, it is straightforward code like Quicksort, write it down, and inefficient, and many ways to implement. Like even having a slightest division may cause surprisingly bad results, and not stable as it does not specify the order of identical keys, and hard to write correctly. And here is some simple code and easy version of n-place partition to understand, but not unversional form. Better partition. In better partition, want to partition an array A left to right. In first, get the pivot element out of the way, but swapping it with an last element, and let I start at the first element and J start at next to last element. I is equals to left and J is equals to right minus 1. As you see here, I is in the left side of first order and J is in right minus 1 place. Next, with duplicate elements, here the partitioning for the so far defined as ambiguous for duplicate elements. The equality is included for the both sets, and it is randomness makes a balance distribution of duplicate elements, and when all elements are identical, the both I and j steps may swaps. But crossing the middle, the partition balanced, so it's n log n. Next, the better pivot. Here, it uses the median of an array, like partitioning the away cuts and into rough off. Next, and an optimal quicksort is log n log n, and however the hard to find to exact median. And here are some examples, like sorting an array to pick a value in the middle, and approximation to extract the median. Here, as you see here, here is the algorithm, like see in A of left, the element is 2, and in center 13 is placed, and in right element is 6. So here the swap order is like swap a center and A of right, and choosing a center as pivot. That means the element 6, it is swapped to pivot, and A of right minus 1, like the center element 6, it is swapped to right side of right minus 1. That means right element is 13, as right minus 1 is 19 plus. So here the middle element swaps into 19th place, and 19th element goes into center. So the point to be noted, we only need to partition A of left plus 1 and right minus 2. Small arrays. For every small arrays, Quicksort does not perform as well as insertion sort, and how small depends on many factors, such as time spent making the recursive call, the compiler, and etc. And does not use the Quicksort recursively for small arrays, and instead of using a sorting algorithm that is efficient for small arrays, and such as insertion sort. Quicksort analysis: assumption, runtime, and some other constants. And here assumptions are like a random pivot, no median of 3 partitioning, and no cutoff of small arrays. Runtime: here in runtime, the pivot selection and runtime and partitioning are to be noted. In pivot selection, constant time, that is 0 of 1, and in partitioning the linear time, that is O of n. In runtime of the 2 recursive call, and here the C is constant, that is here is the basic formula, like T of n is equals to T of I plus T of n minus 1 plus j plus I n minus 1 n minus 1 and plus Cn, where C is constant and I is the element of n is 1. The worst case analysis, like what will be the worst case. The pivot is smallest element, that all the time it is a partition is always unbalanced, as you see here. In this case, the partition is perfect balanced, and pivot is always in middle, as you see here. Average case analysis like assumption, each of the sizes of S1 is equally likely, and this assumption is valid for providing median for 3 strategy, and on average the runtime is n log n covered in comp 271. Thank you. Please do subscribe, and here are one more slide left. Quicksort for faster than Quicksort. Quicksort is faster than Quicksort, but in both the Quicksort and Quicksort are like n log n in average case. Why is Quicksort is faster than Quicksort? In the loop of consists of increment and decrement by one which is faster. Test in HM. There is no extra uniting as in Quicksort. So here what you see in inner loop. Thank you. Please do subscribe and like.